Okay, let's unpack this. You know that feeling when you're clicking through links, scrolling through endless feeds, or maybe hailing a ride with an app, and you just think, how on earth does all this actually work?
Uh-huh.
It feels like magic, but it's definitely not.
That's right. And that feeling of being slightly, well, maybe overwhelmed by the sheer scale and complexity of these online services is exactly what we're tackling today in the deep dive.
Right.
You've shared some fascinating material with us, notes and insights around system design interviews, and our mission is to kind of cut through the noise and pull out the core principles that make these massive systems tick.
Like a backstage pass.
Think of it as giving you a backstage pass to how the internet's biggest players operate.
Yeah. Consider this your shortcut to being in the know.
Mm.
We're going to explore ideas that might sound a bit technical at first. Things like the CAP theorem and why picking a database is a fundamental trade-off. The difference between simply getting bigger machines versus adding more of them.
Right, scaling.
How all the internet traffic gets managed without everything crashing, and the clever ways they handle truly massive amounts of data.
Exactly. We'll also be looking at the vital role of caching, that smart technique that makes everything feel so much faster, and how content delivery networks strategically place servers around the globe to bring information closer to you.
Okay.
Our goal isn't to make you a system architect overnight, obviously, but to give you those aha moments, those insights that suddenly illuminate how these digital giants function so smoothly in the background of your daily life without overwhelming you with jargon.
So let's dive right into a foundational concept, the CAP theorem. Now, when I first encountered this, it sounded almost like a secret code.
Yeah, it kind of does.
But it's actually a really insightful way to understand the inherent challenges in building systems that operate across multiple computers.
What's fascinating here is how the CAP theorem boils down to three key guarantees that any distributed system strives for: consistency, availability, and partition tolerance.
Okay, 3 pillars.
Yeah, think of it like trying to have a perfect group chat with your friends. Consistency means everyone sees the same messages at the exact same time.
Right, perfectly synced.
Availability means the chat is always up and running. You can always send and receive messages. It's just available.
Makes sense.
And partition tolerance means the chat keeps going even if some people temporarily lose their internet connection. The network gets partitioned.
Okay.
You want all three, but the theorem states you can realistically only fully achieve 2 out of the 3 perfectly. There's always a trade-off.
Right, so it's an inherent trade-off. You can't have that perfect group chat where everyone is always in sync and always online, especially when internet connections can be, well, unreliable. Something has to give.
Precisely. And in the world of databases, this trade-off is critical. Traditional relational database management systems, or RDBMS, like, say, MySQL or PostgreSQL, often prioritize consistency and availability. They aim to give you the most up-to-date information and be generally very reliable, but might struggle a bit if there are major network disruptions between parts of the system. So when the sources you share talk about needing strong data accuracy,
Like banking.
exactly, these types of databases are often the go-to.
Okay, that makes sense for things where accuracy is absolutely key,
Yeah.
like those banking transactions. You definitely don't want to see different balances on your account at different times. No way.
Absolutely. On the other hand, you've got NoSQL databases like MongoDB or perhaps Redis. They might lean towards consistency and partition tolerance.
So they handle network breaks better.
They're designed to handle network issues more gracefully, ensuring the system stays operational, but there might be brief periods where the data isn't perfectly in sync across all parts of the system. Eventual consistency, they sometimes call it.
Okay, eventual. And then there's a third option.
Yeah, then you have databases like Cassandra or DynamoDB. These often prioritize availability and partition tolerance, the AP systems. They're built to be incredibly resilient and always accessible, even if it means occasionally serving slightly older information for a very short time. So it really boils down to what you, as the system builder, need most. Is it rock-solid data accuracy, or is it virtually guaranteed uptime?
Got it. The system has different needs.
Exactly. The CAP theorem forces you to make those fundamental architectural choices right from the start. So when the sources you shared talk about, say, a URL shortener needing to be highly available and partition tolerant, even if it means occasional, very brief inconsistencies in redirect counts,
Yeah.
the CAP theorem clarifies why they'd lean towards an AP availability and partition tolerance database.
Okay, we've got this core idea of unavoidable trade-offs.
Yeah.
That's clear now. Now let's talk about handling more and more users and, exponentially growing amounts of data, this concept of scaling. I always hear about scaling up and scaling out. Can you break that down in a way that really sticks?
Sure. Think of it like running a restaurant. Vertical scaling, or scaling up, is like buying a much bigger oven or a larger grill for your existing kitchen.
Okay, upgrading the current equipment.
Exactly. You're upgrading your current resources, the single machine, to handle more demand. Horizontal scaling, or scaling out on the other hand, is like opening a whole new branch of your restaurant.
Adding more locations.
You're adding more independent locations, more machines to serve more customers.
That restaurant analogy really clicks. So vertical scaling seems simpler on the surface, right? You're just dealing with one main machine, albeit a more powerful one.
Yes, it's often simpler to implement initially. You don't have the complexities of distributing data and managing multiple independent machines. However,
Good catch.
well, yeah, there's a natural limit to how big that single oven can get, right? You hit a ceiling. Plus, if that one big machine fails,
Everything stops.
your entire system goes down. It creates a single point of failure, which is usually bad.
Whereas with horizontal scaling, if one of your restaurant branches has an issue, maybe a power outage or something,
Right.
the others can still keep serving customers. But it sounds significantly more complicated to manage all those different locations.
It is more complex, no doubt. You need systems like load balancers, which we'll get to direct traffic to the available servers. And you need to think carefully about how data is shared or replicated across them.
Okay.
But the upside is almost limitless scalability, at least in theory, and much, much better resilience. Web servers and what are known as microservices.
Where you break the app into small pieces.
Exactly, where an application is broken down into many small independent services. Those are prime examples of systems that almost always scale horizontally.
And vertical. Is it ever used?
Oh, yeah. Some databases or older applications where all the different parts are bundled together. Monolithic apps might still lean towards vertical scaling, especially when the workload is difficult to break down into independent parts.
But for the big guys,
For the big guys, the core insight here is that modern internet giants almost universally choose the complexity of scaling out because the limitations and, critically, the single point of failure of scaling up just become unacceptable at their size.
so scaling is all about being able to handle more load, right? More users.
Yeah.
But how does that directly relate to how fast things are for the user? Are they the same thing?
That's a really crucial distinction. They're related, but not the same. Performance is about how efficiently your system handles individual requests with its current resources. How quickly can that single oven bake a pizza, so to speak?
Okay, the speed of one task.
Right. Scalability is about maintaining that level of performance as the number of customers dramatically increases. A system can have great performance for, say, 10 users, but completely fall apart when 10,000 try to use it simultaneously.
Like that small local bakery you mentioned.
Exactly. Makes amazing cakes, but just can't handle hundreds of orders at once. It doesn't scale well. Okay, like a website that loads lightning fast when you're the only one on it, but then grinds to a halt during a big online sale.
Precisely. That website isn't scalable even if its baseline performance is good. When we talk about system performance in this context, we often look at key metrics like latency.
How long a request takes.
Yeah, the time it takes for a single request to be processed. Then there's throughput, which is the number of requests the system can handle in a given time, less requests per second.
Okay.
And availability, which is simply the percentage of time the system is actually up and running. Your scaling choices, horizontal versus vertical, have a direct impact on all these metrics.
Okay, so you've potentially got all these servers running because you scaled out horizontally to handle the load. How do you make sure the incoming traffic, all those user requests, is spread out evenly so no single server gets completely overwhelmed?
Good question.
That sounds like a job for a load balancer.
You nailed it.
Yeah.
Think of a load balancer as like a traffic cop for the internet. It sits in front of your group of servers, the ones you added for horizontal scaling.
Exactly. And it intelligently distributes incoming requests across those multiple machines.
So if a huge number of people suddenly try to access a popular website, the load balancer steps in and says, okay, you go to server 1, you go to server 2, you go to server 3.
Precisely. It spreads the load. And the benefits are pretty significant. Firstly, high availability. Like we said, if one server happens to go down for maintenance or crashes.
The load balancer just stops sending traffic there.
Exactly. It routes everything to the healthy servers. Users might not even notice. Secondly, scalability. As we discussed with horizontal scaling, it allows you to easily add or remove servers behind the load balancer as your traffic grows or shrinks.
Makes sense.
Thirdly, it improves efficiency by making sure no single server becomes a bottleneck while others are idle. It can even help reduce latency sometimes by directing users to the server that's geographically closest, perhaps, or maybe the one with the fastest current response time. And modern load balancers often offer security features too, like handling SSL encryption or helping to fend off certain types of malicious attacks like DDoS.
Wow. Okay. So it's doing quite a lot. It's not just randomly sending traffic around then. There are actually different strategies or like algorithms a load balancer can use to decide where to send each request, right?
Absolutely. There are various algorithms. A really simple one is round robin, where it just cycles through the available servers in order. Server 1, then 2, then 3, then back to 1.
Okay. Simple enough.
Another very common one is least connections. This one's smarter. It sends the new request to the server that currently has the fewest active connections.
Ah, so it tries to balance the actual workload.
Exactly. It helps prevent one busy server from getting totally overloaded while others are just sitting there bored. More sophisticated algorithms might look at server response times or even use something called hashing based on the user's IP address to try and ensure that the same user consistently connects to the same server, which can be important for some applications that maintain session state.
Got it.
The fundamental idea, though, across all these methods, is always about distributing the load in an intelligent, efficient way.
Okay, so now our application spread across multiple servers thanks to horizontal scaling, and the traffic is being smartly managed by load balancers. Great, but what about the actual database that holds all the information? If you have a truly massive amount of data, like petabytes, can one giant database possibly handle all of that efficiently?
Yeah, that's where sharding comes into play. It's a common solution. Imagine trying to organize a massive library with millions upon millions of books. It would be incredibly inefficient to have them all piled up in one giant room.
Totally. You'd never find anything.
Right, sharding is like breaking that library down by subject, maybe fiction in this wing, nonfiction over there, periodicals in another room, and then putting each subject's books into different smaller rooms.
Okay.
In database terms, you're breaking your single large database into smaller, more manageable chunks called shards. And each shard typically lives on its own independent machine, its own server.
So instead of one enormous monolithic database that's struggling, you end up with a collection of smaller independent databases, each holding a specific slice, like a subset of the total data.
Exactly. Maybe you shard by a user ID range or geographic region or some other logical key, and this allows for parallel processing. When you need to access specific data, say for user number 12345, you know exactly which shard holds that user's information.
So you only query that one small database shard.
Precisely, which
Yeah.
is significantly faster than having to search through a massive monolithic database containing all the users. It becomes pretty much essential for applications dealing with truly enormous datasets or very high volumes of transactions like reads and writes.
But does it make things more complicated?
Oh, definitely. A key challenge with sharding, as your sources likely hinted at, is managing things like transactions or queries that need to involve data sitting across multiple shards. That gets complex.
Now, you also mentioned partitioning. Is that essentially the same thing as sharding? They sound similar.
That's a common point of confusion. Partitioning is a broader concept. It just means dividing a database, or even just a table within a database, into smaller, more manageable pieces. Sharding is a specific type of partitioning.
Okay.
Specifically, it's horizontal partitioning, where you're dividing the rows of your database tables across multiple independent database instances, which are almost always on different physical machines. That's the key for scaling.
So partitioning is the general idea. Sharding is a specific spread it across machines version.
Pretty much. You can also have vertical partitioning, where you split a single table with many columns into multiple tables, each with fewer columns. But when people talk about scaling massive databases, they usually mean sharding that horizontal split across multiple machines. Think of it this way. While all sharding is a form of horizontal partitioning, the key differentiator is that sharding always involves distributing data across independent database instances, usually on separate machines, to significantly improve performance and scalability for very large data sets.
Okay, so sharding is a specific type of horizontal partitioning that's all about spreading data across different machines to really boost performance for massive data sets, even if it, introduces complexities in managing data consistency across those shards.
Precisely. While managing data consistency in transactions across multiple shards can be a complex undertaking, no doubt, for many of today's largest scale applications, the significant performance benefits you get from sharding far outweigh those added complexities. It's often the only way to handle the sheer volume.
Now, we've discussed strategies for making things faster with load balancers and for handling enormous amounts of data with sharding. But what about when users repeatedly access the exact same information over and over? It seems wasteful to keep hitting the database, even a sharded one, every single time.
Yeah, absolutely wasteful.
That's where the concept of caching comes in, right?
You're spot on. Caching is absolutely fundamental for performance. It's like keeping your most frequently used kitchen tools, your favorite knife, your spatula, the salt shaker right there on the countertop.
Instead of in the back of the pantry.
Exactly. Instead of having to dig through drawers in the pantry every single time you need them. In computing, caching refers to storing frequently accessed data in a much faster temporary storage layer, the cache, so the system can retrieve it very, very quickly without having to go back to the slower primary data store, which is typically a database.
That makes perfect sense. So if a large number of users are constantly viewing the same popular product page on an e-commerce site, the system can just grab that page's information from the superfast cache instead of repeatedly querying the main product database.
Exactly. The difference in speed can be orders of magnitude. And there are several different strategies for how and when the data in the cache actually gets updated, because of course the original data might change.
Right, the price might change or something.
Precisely. One very common approach is called cache aside, sometimes referred to as lazy loading.
Lazy loading.
Yeah. With this strategy, the application checks the cache first when it needs data. If the data is found there, that's called a cache hit. Great. It's served directly to the user super fast.
And if it's not there?
If the data isn't in the cache, a cache miss, the application then fetches the data from the main database, serves it to the user, and also puts a copy of that data into the cache for next time.
Okay, so it only caches data that's actually been requested. That seems pretty efficient. But what happens if the original data in the database gets updated, like the price changes? The cache could then be holding old, inaccurate information, right? Stale data.
That's the crucial trade-off. With the cache aside approach, the possibility of serving stale data until the cache entry expires or is explicitly invalidated. Another strategy called write-through aims to minimize this.
How does that work?
With write-through, you update both the cache and the database simultaneously every time data is written or changed.
So they stay in sync.
Yes, this ensures stronger consistency between the cache and the database, but the downside is it can make write operations somewhat slower because you have to write to two places, and you might end up caching data that isn't actually accessed very often, potentially wasting cache memory.
Okay, so it's the familiar trade-off again, isn't it? Consistency versus speed, or maybe write speed in this case. What are some other common caching strategies?
Another approach is write behind, sometimes called write back. With this, when data is updated, it's written to the fast cache first, and the application immediately tells the user, okay, done. Then, the cache updates the underlying database asynchronously, like after a short delay.
Oh, so writes feel really fast to the user.
Very fast writes, yes. But it does introduce a potential risk. What if the cache fails before those changes are successfully written back to the permanent database? You could lose data.
Ooh, yeah, that sounds risky for important stuff.
It can be. You need mechanisms to handle that. Finally, there's refresh ahead. Here, the system proactively tries to predict when cached data might become stale or expire, and it refreshes it in the cache before it actually expires or before a user asks for it again.
So it tries to anticipate needs.
Right. This can lead to faster access for frequently used data because it's more likely to be fresh when requested. But the downside is it can also waste resources if it refreshes data that isn't subsequently needed. The optimal strategy really depends heavily on the specific requirements of the application, how critical is strong, immediate data consistency versus the need for extremely low latency and fast writes. Financial data needs different handling than, say, social media post counts.
This is really insightful. It's clear that all these choices, cache aside, write through, write behind, they're very deliberate and based entirely on what the specific application needs to prioritize.
Yeah.
Consistency, speed, write performance, data safety.
Absolutely.
Okay, now the final piece of the puzzle for making our online experiences feel fast and responsive, especially when we're accessing content from servers located really far away. is the use of content delivery networks, or CDNs, right?
Absolutely. Content delivery networks, CDNs, are just fundamental technology for delivering fast internet experiences today, especially globally. Think of them as having multiple copies of a popular magazine. In this case, website content like images or videos strategically stored in local newsstands all around the globe, instead of everyone having to order it directly from one central publisher way over on the other side of the world.
So the CDN is like the network of newsstands.
Exactly. A CDN is a network of geographically distributed servers, often called edge servers, that are designed to deliver content to users from the server that is physically closest to their current location.
So if I'm sitting here in, say, London, and I access a website whose main servers, the origin servers, are located way over in California,
Mm-hmm.
the CDN will likely serve me the website's content, the images, the videos, the style sheets, from a server located somewhere much closer, like maybe in Europe, maybe even the UK.
Exactly right. CDNs primarily handle static content, things that don't change constantly for every user. Images, videos, CSS style sheets, JavaScript files. By serving this content from geographically closer servers, they dramatically reduce latency, the time it takes for the data to travel.
And less travel time means faster loading.
Directly translates to faster loading times for you. Plus, they significantly reduce the load on the origin server, the main website host, because it doesn't have to serve every single image to every single user worldwide.
That must save the main server a lot of work.
A huge amount. And because the content is replicated across multiple locations in the CDN network, it also improves the overall availability. If one CDN server has an issue, another nearby one can often take over. And they can even offer some built-in security benefits, like helping to absorb sudden surges in traffic, sometimes called DDoS attacks.
And there are different ways that content actually gets onto these CDN servers in the first place, right? You mentioned the concepts of push and pull. Can you quickly explain those?
Yeah, sure. With a push CDN, the website owner actively uploads or pushes their content directly to the CDN servers whenever that content is updated. You explicitly tell the CDN, here's the new version of this image.
Okay, so you manage it directly.
Right. This approach is well suited for content that doesn't change very frequently, maybe large video files or software downloads. With a pull CDN, it's more automatic. When a user requests content, say an image, for the very first time in a specific region.
The local CDN server doesn't have it yet.
Right. So the CDN server that is closest to that user will pull that specific image from the origin server, deliver it to the user, and then cache it locally on that edge server.
Ah, so it caches it after the first request in that region.
Exactly. Then, subsequent requests from other users in the same geographic area for that same image will be served directly from the local CDN cache, nice and fast. This method works really well for sites with content that might be updated more frequently, like website images or CSS files.
So pull's more automated, push gives more control.
That's a good way to put it. Ultimately, a CDN becomes pretty much essential for any online service that has a global user base, serves a lot of static content like media, and has a critical need for both speed and reliability. You pretty much can't run a major global site without one today.
It's really amazing to see how all these seemingly disparate pieces, the CAP theorem guiding those initial crucial database choices. The different scaling strategies, horizontal versus vertical for handling user growth, load balancers acting as those indispensable traffic managers, sharding for managing truly massive databases, caching for that lightning-fast access to frequently used data, and then CDNs providing global reach and speed, how they all come together in a coordinated way to create the online experiences that we often just take for granted every single day.
Absolutely. It's like a complex, well-orchestrated machine running behind the curtain. And once you have this foundational understanding, when you think about your own daily interactions online, you can actually start to recognize these principles at work.
Yeah, like how?
Well, ever wonder why that website with servers halfway around the world loads almost instantly for you?
Yeah, all the time.
That's very likely a CDN doing its job, serving content from nearby, or when a major social media platform experiences a brief hiccup, maybe some features are slow, but the whole thing doesn't collapse.
Right, degrades gracefully, sort of.
Exactly. That underlying resilience is built upon principles like horizontal scaling and intelligent load balancing, ensuring that failures are isolated and don't bring everything down.
It's so true. And when we consider the example systems we briefly touched on from your materials, like a simple URL shortener fundamentally needs a very fast and highly scalable database, probably a NoSQL option focusing on availability and partition tolerance, right?
Right.
Coupled with aggressive caching for those frequent redirection requests, you hit the cache most of the time.
Exactly. Speed and availability are key there. Then you take something much more complex, like a newsfeed system.
Like Facebook or Twitter's feed.
Right. That has to tackle the significant challenges of scaling both the reading and the writing of data. Generating those feeds for millions of users is tough. So you see sophisticated caching mechanisms, potentially sharding user data, maybe complex fan-out strategies for distributing posts, and heavy reliance on CDNs to deliver all that rich media content, photos, videos quickly.
Yeah, the scale is mind-boggling.
It really is.
Yeah.
And then a real-time ride-sharing application that's critically dependent on highly accurate location services, often using things like geospatial indexing in the database. It needs the ability to provide real-time updates to users, maybe using WebSockets.
So you see the car moving on the map.
Exactly. And it requires very careful considerations around data consistency in a highly distributed and constantly changing environment. You need to know accurately where drivers and riders are and match them efficiently.
Wow.
Precisely. Each different type of online application has its own unique set of challenges and constraints and performance requirements that ultimately dictate which of these fundamental sister design principles become the absolute most critical for its successful operation. The trade-offs they choose define the system.
So to bring it all together for you, our listener, you now hopefully have a solid foundational understanding of the core principles: CAP, scaling, load balancing, sharding, caching, CDNs that enable these massive online systems to function with such, well, apparent ease and reliability.
Yeah.
Hopefully it's no longer quite the mysterious black box it might have seemed before.
And this knowledge, even at a high level, truly provides you with a powerful new lens through which to understand the technology that you interact with every single day. You've moved beyond simply using these services to understanding, at least conceptually, how they actually work behind the scenes. It demystifies things a bit.
Definitely. So the next time you're using a popular app or browsing a website, maybe take a moment to think about which of these underlying design principles might be at play. What kind of trade-offs do you imagine the engineers might have had to consider when they built it?
Yeah, like why did they choose that type of database or that caching strategy?
Exactly. And how would the very specific requirements of, say, a super secure online banking application influence their technology choices compared to something like a social media platform that prioritizes constant updates and maybe tolerates slight delays?
It forces you to think about the requirements first.
It's a vast and endlessly fascinating world, system design. And hopefully this deep dive has maybe ignited your curiosity to continue exploring even further if you're interested. There's always more to learn.